Welcome to this section. In this section 2, we will discuss about the maximum geodesic. Last class we have seen that the existence of the maximum geodesic, and we have seen that first of all we have wrote alpha double dot of t is equal to first of all we have wrote alpha double dot of t is equal to yeah. First we have seen alpha double dot of t is equal to some g of t into n of alpha of t, n of alpha of t. Then we have found that the function g is defined as alpha double dot of n composition of alpha, and we have seen this further. G of t is equal to um, as minus uh, alpha dot of t dot n composition alpha of t. This was your g of t, and we have substituted this in this equation, and we have got a system of second order differential equation as alpha double dot of t plus alpha dot of t naught t composition n of alpha of n composition. So it is n composition alpha dot of t into n of alpha of t. This is equal to 0, and by using the solution existence and unique of solution of second order differential equation, we have found that there exists a solution for this. About 0 there exists an interval, and if beta 1 from I1 to u of this differential equation satisfy the initial conditions, then we have seen that this solution is unique. We want to prove that the solution is unique. So we have found out the solution, and next we will prove the solution is unique. So moreover, the solution is unique. The solution is unique in the sense that if beta 2 from I2 to U is another solution of 1, our equation 1 was alpha double dot this equation only. So this was your equation 1. So and the solution for equation of 1 with the same condition. So with beta 2 of 0 is equal to P, and the beta 2 dot of 0 is equal to V, for then we will have beta 1 of t is equal to beta 2 of t for every t belongs to I1 intersection I2. So it follows that thus it follows that there exists a maximal open interval. There exists a maximal open interval I I, comma, I is the union of domain of all solutions of equation 1, where I is the union of domains of all solutions of the equation 1, on the equation 1, which maps which maps 0 to b and have initial velocity and have initial velocity v, and a unique solution and a unique solution alpha from I to u of 1 satisfying alpha of 0 is equal to p and alpha dot of 0 is equal to b. Further, if beta from I tilde to u is another solution of the equation 1 with beta of 0 is equal to p and beta dot 0 is equal to v, then for I tilde contained in I and beta is the restriction of alpha is the restriction of alpha to I tilde. So beta is the restriction of alpha to b tilde. Now to complete this proof, we want to prove that alpha is actually a curve in S. So to complete the proof, because we have assumed del f of p not equal to 0 for every p belongs to u and dot, and we haven't checked that alpha belongs to surface or not. That's it. To complete the proof, it remains only to show that it remains only to show that the solution alpha of 1 is actually a curve in S. Is actually a curve in S. For if so, it must be a geodesic. A geodesic. Since it satisfies the geodesic equation 1, satisfy the geodesic equation 1, and the rest of the theorem follows from the uniqueness statement above. To show that alpha in fact a curve in S, to show that alpha is in fact a curve in S, let alpha from I to U be a solution of 1, a solution of 1, then alpha dot n composition alpha dash is equal to alpha double dot n composition alpha plus alpha dot n composition alpha dot, and which is equal to 0 by equation 1. Hence alpha dot n composition alpha n composition alpha is constant along alpha, is constant along alpha. Now alpha dot n composition alpha of 0 is equal to alpha dot 0 dot n composition alpha of 0, which is equal to v dot n of p. Now this is equal to one belongs to the tangent space and another belongs to the normal space, so this dot product is 0. So we must have, so we must have alpha dot of t dot n of alpha of t is equal to 0 for every t belongs to I. By chain rule, F composition alpha dash of t is equal to del of f of alpha of t dot alpha dot of t, and this is equal to norm of del f of alpha of t is the norm into n of alpha of t dot alpha dot of t. That's equal to 0 for every t belongs to I. Thus F composition alpha is constant along alpha, but F composition alpha of 0 is equal to f of alpha of 0, that's equal to f of p, and that's equal to c. So we must have f of alpha of t is equal to c for every t belongs to I, which implies alpha of t belongs to f inverse of c for every t belongs to I, which implies image alpha is contained in f inverse of c, that's equal to s. So which implies this completes this completes the proof. So we have proved that alpha is belongs to s. Now here is a remark. It follows from above theorem that follows from above theorem that each maximal geodesic each maximal geodesic on the two sphere in R3 is either a great circle, you can see this in example 3, is either a great circle or is constant since such a curve can be found through since such a curve can be found through each point P with any given initial velocity. Any given initial velocity. Similarly, that means the first one says that uh, each maximal geodesic, if you're considering on the two sphere in R3, that's our sphere itself, is either is going to be a great circle or is a constant. So similarly, each maximal geodesic on the cylinder x1 square plus x2 square equal to 1 in R3. This already we have seen in your example. So see your example 2. Example 2 is either a vertical line We have seen this as the case a equal to 0 and c equal to 0, then a and c not equal to 0, something like that. So vertical line, comma, a horizontal circle, a helix, comma, a helix, comma, spiral, or is constant, or is constant. Thus, we have seen what's a geodesic and how to prove some given curve is going to be a geodesic. And the last one, we have seen the theorem that the existence and uniqueness of a maximal geodesic. So with this chapter closes here. Next class onwards, we can discuss about the parallel transport. So thank you for your patient listening. Thank you.